is Hernan Julio, and I will be your tour guide, virtual tour guide today for La Silla Observatory. So, welcome from wherever you are in the world, and we would like to invite you to greeting us through the with your comment in Facebook, in YouTube, and also your question. If you have a question, please go ahead and we will be very nice, pleased to answer you. As I told you, my name is Hernan Julio, and I'm a journalist specialized in astronomy. And today I'm also with Felipe Zurita. Felipe is a physicist, is a astronomist,
Astor.
astronomers. So please, Felipe, hi, how are you?
Hi Hernan. Hi everyone. Hi Sway Grain from Amsterdam. Hi for the new tour guide today is La Silla in English,
Yes.
and every Saturday we have a virtual tour between in Spanish and English. Today is English. In the next week is a Spanish impanel, I think. So I hope you enjoyed today the first of the all the first telescope of Observatory of ESO.
All right. Thank you very much, Felipe. Well, we want to welcome you to, as Felipe said, La Silla Observatory. And we go right away to know what is ESO. ESO is the European Southern Observatory. In your screen, you will have the you will have the countries that are part of ESO. As you can see, most of them are in the Europe continent. Okay, we have Denmark, the Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, Czech Republic, Austria, Switzerland, and Italy. And we have Australia, which of course is not in Europe, which is our strategic partner, and Chile, which is the host country. All the telescope for Europe are in Chile. Well, ESO is an international organization who was began in 1962, arrived in Chile with only 5 countries, the first 5 countries that were part of ESO, arrived in Chile in 1963. In 1963, the ESO arrived to Chile, so we just celebrate our 60th anniversary last year. Okay, already the ESO Observatory has various observational facilities. You can see in your screen. We have at your left you have uh, Paranal, which is the VLT and the VLTI in the northern part of the country, and at this little center right you have La Silla. Well, we're talking today about La Silla. We're going to show you La Silla Observatory. This is a classical observatory. Was inaugurated in 1969. Okay, so La Silla is very famous and is still being one of the most productive observatories in the world. In the 90s, ESO built Paranal in the VLT and the VLTI to your left. And as I told, as Felipe said, we also have the same tours, this virtual tour every Saturday in English and Spanish, and also Paranal and La Silla. So next weekend, you can go visit virtually in the same time the VLT. And in Paranal, we have also 2 other telescopes, the VST, which is and Vista, which are 2 important mapping telescopes. And there is 2 telescopes in construction. We have the ELT, the famous already ELT, the extremely large telescope. This is going to be one of the biggest telescope on the world in the next decade. The ELT is only at 20 kilometers from Paranal. Actually, it's going to be operated from Paranal. That's why the ELT is important. It's in the middle of the construction right now. As I told you, will be the biggest eye looking to the sky in the surface of our planet. Also, you can see to the left down in the down part, a picture of the CTA, the Cherenkov telescope arrays. Very special telescope, are about 100 telescopes, 99 telescopes, who are capturing the gamma ray burst. And they are also very close to Paranal, and the ELT is in the same area, okay? Only 10 kilometers from Paranal. So in the next decade, we're going to have this enormous telescope over there near Paranal, the ELT, and the CTA South. But also, as you may know, we have at your right, you can see ALMA telescopes. ALMA is the Atacama Large Millimetric Array. It's the biggest radio telescope in the world. It's about 5,050 meters above the sea in the Chilean altiplanic. Shangnan Tor is the name of the plateau where these 66 antennas are. These 66 antennas also can have different configurations. The biggest configuration that they can get is 16 kilometers. It's really amazing. Yeah, and it's the biggest radio telescope in the world. And down at your right, you can see APEX, the Atacama Pax Finder experiment. Is one antenna. This antenna, APEX, is 100% ESO. And this antenna is only 12 meters diameter. The ALMA antennas are also 12-meter diameter, but they are 66. And ALMA is a consortium also. It's an international organization. And one of the partners there is ESO. Okay, ALMA is not 100% ESO. It's ESO with United States, North America, and also Japan and some other countries. Well, this is what is ESO, the facilities, observational facilities of ESO in Chile. And I think we'll go right away to La Silla, yes. Well, from Europe, in your screen, you can see the maps of the countries who are part of ESO. And we have to travel to La Silla Observatory. From Europe, we have to cross the Atlantic Ocean and go to South America. The European in the 60s, in the beginning of the 60s and in the beginning of the 60s, they start to look for a place where to build big telescope, okay? Telescope bigger than 1-2 meters in those days. They look in the southern hemisphere because they didn't have this big telescope in the southern hemisphere, and that's why they look a place in the southern hemisphere. They look in Australia, also in Africa, but they find out that Chile has one of the driest deserts in the world. That's the reason why they came to Chile. Now we are arriving in this overflying view, the Andes Mountain. We're crossing down the mountains and we go direct to the Atacama Desert, the southern part of the Atacama Desert, and we can see La Silla Observatory. There we go. That's La Silla Observatory, and you can see now we're going to have a flyover with a drone over La Silla, and you will see different telescopes that we have. We have about 14 domes. This is Danish 1.54 meter telescope. ECTRAs are very new telescopes. Okay, the ECTRAs are looking for extrasolar planets. And we have the 2.2 meter telescope, which today is just Max Planck Institute telescopes. Okay. The 1.5 meter, the 1 meter Schmidt camera now is, as most of the telescope in La Silla, a robotic telescope. And the NTT, the famous NTT, the New Technology Telescope, we can say is the father of all the telescopes with new technology. And CEST also is a radio telescope, the first radio telescope in the southern hemisphere, 15 meters. We will talk a little bit about that later. And the Swiss meter, the 1.2 meters, the telescope, very important in the planetary, extrasolar planetary hunting. And of course, the 3.6 meter telescope, which is the biggest telescope in La Silla, and the one that we are going to visit. So I think it's time to go down to visit La Silla. Give me 1 second, please. Here we are. Let me just give you a panoramic view of this, which is an amazing place. Here we are looking at La Silla Observatory. We are at 2,400 meters above the sea. By the way, we're looking to the west. In this part of the observatory, in this paved way, in this way, in the July 2nd, 2019, we have the solar total eclipse in Chile. Okay, and here we have, for the first time in the La Silla history, 1,000 people. We invite 1,000 people to be with us to just join the eclipse. But you can see now. I will let you enjoy this view a little bit. Now we're looking to the west, to the east, to the mountains, to the Andes Mountains at the sunset. You can see how gorgeous is the view of the mountains. Behind those mountains is Argentina. We have a borderline. Our Andes Mountains is the borderline with Argentina. And of course, we're going back in 360-degree view, and we can see the 3.6. This is the 3.6 telescope, and what we're going to do is go right away inside of this. It's an old-fashioned telescope. It's a classical telescope. It's about 50 meters high. The telescope, the dome, is where the telescope is, and we go inside of the dome right away. Here we are inside of the telescope. Hope you have a good view of this. Let me show you how big is the telescope. It's really amazing. There we go. That's the dome. The dome is about more than 300 tons. Okay, it's a classical dome, as you can see, and also the telescope is a classical telescope. Why is that? Because it has this equatorial mount. The blue part that you are seeing here is the equatorial mount. What that means that the telescope, this blue part, is like a fork who is holding the telescope, which is this light blue part. Okay, this light blue part is the telescope, and the most important, the heart of the telescope is the mirror. Here you have the mirror right here. Let me show you. This round thing is the mirror. The mirror is also a classical mirror with a ceramic, and the mirror is 3.6 meter in diameter. Okay, how this works? How we get the light of the stars? Well, first of all, as you see, we have to open a window in the night. Of course, this picture is during the day, just to make the picture, and we have to open a window. You can see that window, the enclosure, the dome is open right here. Okay, and this white part is the window or the opening of the dome, and that then we have to point to that place, to that window, the telescope. Okay, so we point to our star, the star that we want to watch, we want to observe, and the light will go inside straight to the main mirror right here. The main mirror is curved, okay, and has an aluminum layer who reflect the light, and that light will be reflected to the secondary mirror here. Inside of the secondary mirror, inside of this tube that you see, this black tube up here, is the mirror, the secondary mirror. So the light will go from the first mirror to the secondary mirror, and from the secondary mirror will be reflected back to here, to this cage that you can see down here. What is in here in the cage? Well, there we have the fiber optic who get the light and is sending the information, the scientific information, to the instrument. Okay, in this case the instrument is HARP and NIRPS. Okay, I will tell you a little bit about the instrument, but I just want to make clear how the telescope capture the light. I will go to the main mirror, go next to this reflected to the secondary mirror, and then back to this case where we have the terminals of the instrument, which the fiber optic, who send information, the data, scientific data, to the instrument. Let's take a look from the top of this telescope to have a better idea. Here we go. See, from the main mirror, the light is reflected to the secondary mirror and go back, okay, through this. Well, this, because it's day, it's closed. This is like a camera. Okay, this shutter is closed when the light is open, so the light go back and go to the case. That's the way how it works. Now, it's very interesting to see this man here. Okay, let's take a look to see. We can see this. Could be an engineer. He's taking care of the telescope, and you can see how small he looks in comparison with the Holder telescope. This is the view of the telescope of this 3.6 meter telescope. Okay, it's one of the biggest. Was one of the biggest telescope in the southern hemispheres until the 90s. Okay, 3.6 meter. We call the 4-meter class telescope. Okay. Well, so what we do with this telescope today? Well, this telescope is very famous because it has done for many years bigger discoveries, important discoveries, and today is we can say extrasolar planet hunter. Okay, because it has an instrument which can detect planets around other stars. Extrasolar planets, that's what it means that can detect planets around other stars, not our star. We got planet to our planet, the planet from our solar system. But in this case, this telescope is looking for planets around other stars. That's what we call extrasolar planets, okay? This cannot be seen directly. I don't know if, oh, here we go. We're looking to this video, okay? And what is this video showing us? It's showing how planets is orbiting a star different from our sun. How the instrument detect the planet, we say detect and not to see, because we cannot see the planet, we cannot see the light of the planets. As you can imagine, the light of the star is very strong and the light which is reflected from the planet is very dim, so we cannot see the light from the planet. What we do is to detect the planet around the star, because the planet around the star will pull the star a little bit, okay, because gravity. And what we will see is that the star will go close or far away from us, okay. How we detect that? With the light. You can see the spectrum of the light of that star, and this is an example only. When the spectrum is moving to the left, it's going to the blue, it's going away from us. And when it's moving to the right, it's going, when go blue, go close to us, and when the spectrum moves to the right, to the red, move far away from us. That is why how we know that the star has a planet around, and we can know that the planets, how big is the planet, how far away the planet, how many planets are around the stars. So we call that the radio velocity technique to detect planets. So far, the astronomers have detect more than 5,000 planets around other stars. So it's a very important field in the 21st century. Okay, the first extrasolar planet was found in 1995 by Michel Mayor, an astronomer from Geneva, Swiss, and he won the Nobel Prize in 2011. So please, I don't know if you have any question, Felipe, or if you want to
Uh,
add anything else.
we have a greeting from Amsterdam. Hi,
Oh,
Swain, from far away in in German, and Can you know the concept? Say, can I know this concept? What concept you mean?
Yeah, well,
Eh,
we encourage to the people that is looking at to ask questions. Greetings too, and welcome to know from where you are looking at. Mm,
yes,
okay,
you can
well,
leave the comments. You can leave the questions. Everyone you know about the astronomy, the telescope. Greetings from where you see us. And what is the next? Sorry, sorry, what is the next
yes.
point? The next point to
Oh,
visit.
all right. Well, so we will continue. I want to, well, show you a little bit more of the telescope. Let you know also that this telescope is that you can visit La Silla, and if you visit La Silla, you will go inside, like we are doing now, inside of the telescope. So the visits are every Saturday at 10 o'clock in the morning, and also Sundays at 10 o'clock in the morning. But the Saturday and Sunday is in the winter time, our winter time. That means from April to August. From September to March, we have only Saturday, but in the morning and in the afternoon, 10 o'clock and 2 p.m. So you can go to our web page and an ESO web page, and then from there, look for the link to reserve with the much anticipation, with the in advance, in order to have your ticket, free tickets to go to visit La Silla. All right, let's continue, and we will go to outside again, because we want to visit another telescope. Hmm? Another of the two ESO telescope. As you can see here, some people ask why it's called La Silla. Well, when you are looking to this mountain from far away, from the way, from the highway, for example, you will see this depression here between these hills, to the hill where is the 3.6, and the hill where is the new technology telescope. So, and it looks like a saddle or horse however you want to say, and that's why it's called la silla. Okay, it's not la silla, and it's not a chair; it's a horse chair. All right. Well, we will go to the new technology telescope, which is very important because this telescope is called New Technology Telescope because it's the first one to incorporate all the new technology. First of all, you can see it's very different from the 3.6. You can see that the telescope is smaller, we could say, but it's not smaller. Huh? And we can see that the mirror, for example, here's the mirror, is 3.58, almost 3.6 meter in diameter. Very similar in diameter than the 3.6, but the difference is the technology. First of all, the whole building, okay, it's a different building. We don't have the classical dome, for example. What we have here is a building that rotates in 360 degrees over itself. In order to follow the star, okay, the concept is the same. We have to point the telescope to the star. We open the whole building in this case, in the middle. Okay, this is last door. We open that window, which is actually is we open the whole building from the bottom to the top of the building to the other side of the building, as you can see now, and then we point the telescope, as you can see in the picture. Again, this picture is in the day, but we do all this in the night. So the light from the star will go through the mirror to the mirrors. Here is the main mirror. Now you will understand better the concept of how a telescope works. From the main mirror, the light will be reflected to the secondary mirror. The secondary mirror is up here in this black tube, okay, and we have, you can see a little bit the secondary mirror there, and the light will go back, okay, But in this case, in this new technology telescope, we will have a mirror inside in here. I mean, um, in the middle here, we cannot see it, but there is a third mirror, okay, in 45 degrees. So the light will go from the main mirror to the secondary mirror, will go back, and here the light will go to the right or to the left because will be reflected in the third mirror, which is in 45 degrees. Why we do that? Because the instrument are in the other side of this door. Let me show you the door. Okay, in this room. Okay, there's a room in the back part of this wall. We go inside of this door, and we will be able to see the instrument. Okay, what is an instrument? Well, an instrument is a camera. It's the digital camera. We talk in the other telescope about HARP, for example. HARP is an instrument. It's a spectrograph who is detecting, is analyzing light. Well, an instrument is a digital camera who can make image or can do interferometry, spectrography, which is detect the elements, the chemical elements that are in the star. In that way, we can know through that analysis, we can know what kind of a star we are looking at. See, this is the other door who take us to the other instrument. So again, the light will go from the first mirror to the secondary mirror up here in this black tube, will come back, okay, to the third mirror in the middle, and then from the third mirror we go to the right or to the left. And what is in the right and left side are the instrument. This digital camera, big digital camera, astronomical digital camera, who get the information, the scientific data that the astronomer need, and from here, that information go to the computer room. Okay, let me show another picture of the entity. Here we are. Okay, let's get closer to the mirror. Well, the mirror also is different. The mirror also is a new technology mirror. Okay, it's one of the first mirror in the world that has new technology. First, the mirror is made of cerudur. Cerudur is a new ceramic. Okay, this ceramic cerudur is the low expansion. That means that for first time we could make bigger mirrors. Okay, with the old technology, with the old ceramic, we could make only telescope a mirror to 4 meters in diameter. In this case, with this new cerudur, we can make mirrors of 8 meters in diameter. That's why Paranal are 8.2 meters in diameter, because we first, this was a prototype mirror of 3.58, and the next mirror are the one in Paranal, which has 8.2. So what that means that we can make big mirrors, 8 meter in diameter, for example, but also very thin. Okay, in this case are 28 centimeters. In Paranal are thinner, are only 18 centimeters in thick. That allow us to have this allow us to have this kind of buildings, much more smaller buildings, also building that allow us to make everything easier, and building that allow us to open like you see and now, and that's very good for us because why we open in this way the building, because the wind in the night will go through the building. That means that we don't have different temperature inside and outside. If you come to La Silla or Paranal, as I told you, every Saturday we have these tours. You can book your tour. If you are planning to come to Chile, you can book your tour and visit Paranal and visit La Silla, and you will be inside and you will feel that inside, in the day, inside of the dome is cold. Why that happens? Because we cool down the dome with the cooling system. Actually, there is the cooling system. You can see it. Okay. Why we cool down the dome? Because the dome during the day is closed. And if you keep it closed, the will be heat inside if we don't cool down. And if we don't cool down, that heat will go outside and will produce turbulence, because this warmness, this heat will crash with the atmosphere, a cold atmosphere outside in the night, when the nights come and we have to open the window, we have to open the telescope, and then we will have turbulence around the dome. And the light, the light that is traveling, that we are capturing the night, is traveling for thousands of millions of years from in this empty space. And when this light go inside of our atmosphere, what's happened is that this light get disturbed by the atmosphere. So if we create heat inside of the dome and this heat go outside, will disturb the atmosphere, and that the distortion will disturb the light. That's why we cool down the heat. Also, to know about the mirror is that the mirror is flexible. Oh, how come? Well, as I told you, with this new technology, the mirror is thinner. So right now you're looking to the mirror in what we call parking position. Okay, but in the night the mirror will move. We will have to move the telescope. We will move the mirror, and the surface of the mirror, because it's so flexible, could change a little bit, nanomillimeters. So we have actuators. You can see this down the mirror here. You can see the actuators, and those actuators push up the mirror in order to keep always the surface perfect. Okay, so that's what we call active optic. Active because we have an active mirror who we can move it in the night in order to correct that situation in the surface of the mirror. Okay, physically. Okay, that's what we call active optic. Now, we have also the mirror. Any astronomical mirror has a aluminum surface. Some use silver, but in this case it's aluminum, and the aluminum is the one who reflects. We have to change the aluminum, of course, every 2 years. We take out the mirror from here, and we take it to the base of the 3.6 telescope over there, and from there we what we do is re-illuminize the mirror. We take the all aluminum of the surface of the mirror with a special chemical. We take out the aluminum, and we put the mirror inside of the vacuum, and then we put a new layer of aluminum. That we do every 2 years. We change the aluminum layer of the mirror. The aluminum layers is like a skin, very thin, thinner than a human hair. Okay, and the amount of aluminum that we spend in a mirror is less than the aluminum that is in a Coca-Cola can, for example. All right, I think as I told you that from here we do not the astronomers are not in the night inside of the telescope. They used to be inside. We used to have um, in the third floor of this building, also in the third floor of the other building, the big building, the 3.6, used to be a control room where so every night the astronomers have to go inside of the building and go to the control room and control and receive the information and get the information, the data, the scientific data that they need. But today the control room is far away. Okay, we have learned that we need to put humans and machines away from the telescope in order to do not create during the night heat. That heat that is so bad for us, because that heat will go outside and will produce this turbulence that I already explained you. So I think we have a video of astronomer working in the control room. Maybe you can explain, Felipe, what's going on there.
This is the video of the control room. Let me here. In the right side is a part of a 3.6 telescope, and in the left side is a NTT telescope, the two telescopes showing in a virtual tour. In this place we have a two kind of person. The first one is a black clothes person. This is the operator. They control the telescope, move the telescope, access the telescope to astronomer and work together the astronomer. And the second person work here is the color clothes person is the directly astronomers. The astronomer only get a few nights to use the telescope and work together to with uh, with the with the operator together every night. See the sky, see the sky, take a lot of image of sky, stars, galaxy, nebulas, different objects, celestial objects, depending of the investigation of the astronomer. The astronomer come to the La Silla and tell to the operator what is the work tonight. So let's start in the night. Let's start in the night to preparing the telescopes to see the objects astronomers say. So the principal investigations in ESO starts in this place. So I have a video about the top 10 of the of principal discover of La ESO around the different telescope of La Silla and Paranal. So let me show you the video, and later we come back for a few questions.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way, at 13.2 billion years old. the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
All right, there we have the 10 top discoveries at ESO. Well, we will continue with our tour, and we will leave there's some questions. We will leave the question for the last part of the tour.
Let me see. One question about the 3.6 is: good morning. Why can't find the dozen of planets orbiting Sirius A and B? The reason we can find, I hope find, but can't see directly the planets, because the planet is too shiny to see directly the planets around orbiting the Sirius A and B. This is the why the production of ELT is in over, because I need to see directly the planets to see the atmosphere and the geomorph the planets of around the other stars. And what is the average temperature in La Silla? Average in outside or inside of the telescope? Inside is more cold, and outside is around the. It's different depending on the weather, right?
At the time of the year, we are in a, as you know, we are in the Cordillera. So I was there last Thursday. It was very cold, because we're in the middle of the winter today now. So I said that about the sunset was about 0 degrees. Okay, but in the night it goes down 0. It's not too much maybe for people that lives in countries that are colder than that. Let's go to show you something that people don't see when they come every Saturday to visit us, because the visits are every Saturday, but until 5 p.m. So they cannot see this gorgeous sky that we have here. Look at this, okay? It's really amazing sky, okay? I will explain you a little bit about the sky. First, let's see the northern sky. Some people are from the northern hemisphere. We can see here, for example, we have the Orion belt. Well, this is the whole Orion constellation, Orion belt. We have here, of course, also the Orion nebula, where let's get close to the Orion nebula. This nebula is a cloud of gas and dust where thousands of stars are burning. Okay, and it's upside down because it's a northern constellation, but we are in the south hemisphere, so we see it upside down. The head is down here, one leg is over here, another over here, and so on. And the other constellation, very typical constellation for the northern hemisphere, is this one, which is the Can Majoris, or the big dog. This is Sirius, the eye of the dog. Then we have the back part of the dog. Okay, one leg down here, and the tail, another leg over here. So that's the northern constellation. But let's see something that the people from the northern hemisphere don't see very often, which is the southern sky. Okay, we can see the southern sky, and very quickly, if you are here down in Chile, in the desert, you will see these two clouds. Actually, we call them the Magallanes cloud, but they are not clouds. They are satellite galaxy from us. Okay, these are the only, well, almost the only galaxy that you can see naked eye. From the northern sky, I know that you can see Andromeda, but very, very, very small galaxy. But these are two satellite galaxy from us at the Magallanes cloud, and they're away from us. I mean, they're outside of our own galaxy. They're extragalactic object. The Magallanes cloud are the few extragalactic objects that we can see naked eyed. Okay, and why it's called Magallanes? Because he found them. He discovered them. Actually, the Magallanes cloud, Magallanes, the one who was the first to go around the world in a ship, he navigated in the southern skies, and he used the Magallanes cloud to find the south. How he did that? Well, let me show you. If you make a triangle, okay, with these two Magallanes cloud, you make a triangle here to the left. This angle of the triangle will be the southern celestial pole. In that point is where you have, in the northern hemisphere, you will have the polar star. As you see here, we have a dark spot. We don't have any bright star in that point in the southern celestial pole. What is the southern celestial pole? Is the place where is the point where all the star goes around. Okay, you know that we are now, our planet is turning around itself, and that's why we looks like the stars are moving, but the stars are not moving. We move. Okay. Also, you can use another southern constellation. Here we have, which is the Southern Cross. Okay, here we have the Southern Cross, beautiful. You can take the long stick of the cross and go 1, 2, 3.5, and you will be in the same point where is the southern celestial pole. So you won't get lost if you come to Chile. Because if you see this, if you are one of the spectators that look to this virtual tour, because if you find the southern celestial pole, you can find your way in the southern hemisphere. Okay, you just make a line down and you will have the geographical south. Okay, so if you get lost, you can walk to the south. You will always know where is the south, where is the west, where is the east. Actually, here we can see La Serena light. I think this is La Serena light. Yes, light pollution. Of course, that's a problem that we have in Chile. Light pollution. We will talk about it a little bit. But this is the way to find out the south in southern hemisphere. The other thing is to let you know that we have the original inhabitants of South America. They were great astronomers. Okay, and they, of course, they have this gorgeous sky. The Milky Way. This is the Milky Way. Okay, this bright river in the sky is the Milky Way. Okay, and actually for the people from the Andes, this was a river where many animals went down to have water. Actually, here we can see in this dark spot in the Milky Way, we can see what they used to call the Llama constellation. Can you see it? I pointed out here. Okay, this is the Llama constellation. Okay, and the Llama constellation is a dark spot because it's a cloud of gas and dust so dense that doesn't let the light that are behind it go through it. So you see this dark spot, and if because the Milky Way is so bright that you can see this dark spot all over the Milky Way. And here, for example, they used to see what they call a bird, okay, also the his snake over here. So they see all these animals coming down in this river in the sky to have water. Okay, so as I told you, the people from the original people from South America, they were very good astronomers. Actually, so good that they were here before us. Very close to La Silla, in La Silla site, close to the telescope, we have an archaeological site, okay, from the El Molle culture, where we can see stones, carved stone, where they leave their message to our generation of how they were looking to the sky. All right, I think we have to go down because we're running out of time. We will, here we are in the 3.6, outside of the 3.6 at night. That's the Milky Way, of course. And here we're looking to the Milky Way. And now I will invite you a coffee, okay? We will down at the road, La Silla Road in the night. See, you can see this gorgeous sky, the telescopes. Please come to visit. We are open. We have open doors every Saturday at 10 o'clock in the morning and Sundays at 10 o'clock in the morning from April to August. From September to March, just Saturdays at 10 a.m. and at 2 p.m. Okay. We will go to answer the last question and the last comment with a coffee.
Let me see. We have any more questions? But say thank for your tour. One of the great telescopes from 19th. Yes, the Observatory of Silla is a great one of the 19th telescope in the South Pole. So this is for today.
Yes, we want to invite you to visit our webpage, ESO.org.cl. It's in different language also, and you will find all these pictures. Okay, all the pictures that we show you are in our webpage. Well, actually, here is the photographer of the pictures, one of the photographers who is taking a coffee, and you will be able to take this picture, to use them. They are free. We also have hundreds of videos and news. Okay, all the news about astronomy are always in our webpage. Please follow us in our social media. Okay, as we told you, we have this kind of tour every Saturday in English and Spanish, and also Paraná and La Silla. Today was the La Silla virtual tour. Next week will be Paraná, and will be in English and Spanish too. So we invite you to follow us in our in ESO Astronomy, ESO Chile in Spanish, and also in our YouTube channels. Okay, and please, if you have any question in our social media, in Facebook, for example, we have people who answer the questions. So don't be afraid. Just send your picture, your question, in order to get to know more about this wonderful, wonderful universe, which is astronomy. Well, thank you very much for being with us. And I think this will be all for today. Hope you enjoyed the tour, and we'll see you next time in La Silla o Paraná virtual tour. Thank you very much.
Goodbye, everyone.